Okay. Mm. I hope the other instructor has started that body plot compensator design. So we will solve some problems based on that today.
Okay.
Okay. I have taken few problems. How we are going to approach this is in your end semester exam, your exam will be on computer based mode only. So you won't really solve compensator design based problem in pen and paper. So, but this compensator design based on root locust and bode plot will be there for your design assignment. So two design assignments will be there. First one will be based on root locust based compensator design. The second assignment is on bode based compensator design. Along with that, some state space which is coming in the next few weeks will also be there. So, for design assignment, what you are expected to do is detailed instruction will be posted. A bad side view I'm giving. You are supposed to, we will be giving a question that will be random based on your roll number or any other number. Each one of you will have a unique question, unique data for that question. Question pattern will be same, but data will be different. So based on the data, for example, we may change the transfer function or the steady state error value we are giving. So this kind of changes will be there. Based on that, you have to design a compensator using MATLAB for your particular question. So it will be evaluated based on your question that will be unique. You cannot copy from each other. That's the whole point of that assignment. So it's everything online, nothing offline. Like no need to solve anything by hand, everything by MATLAB, and you can attach the solutions. You have to answer. We will give a answer template. You have to update your answer in the template, attach the MATLAB code along with the plots, and that's how the design assignment will be. So today we will be seeing some questions that can be solved using MATLAB. How you generally calculate phase margin, gain margin, frequencies, and how to design a compensator based on the body plot that we will see today. To start with, we have this first question. So it says, what for the following open loop system in the unity feedback configuration, loop transfer function has been given, open loop transfer function has been given, k into g of s they have given. Right. So for what range of frequencies will the phase margin be greater than 30 degree? They're asking for some values of k. The k gain you have to change so that you will get the overall system's phase margin should be greater than 30. So they have given few options. Let us first solve this in MATLAB and see how it is, what is actual phase margin for k value of 1, and then we can change the k value based on the phase margin we need. Okay, so the question is this. This is the question. I will first type down the question and then we can increase the screen size. Okay, first transfer function 1 will be equal to k into s plus 1 divided by s square into s plus 10 the whole square. Okay, we put one bracket for this whole. That's it. Now k is unknown, s is also unknown for MATLAB. So let us define k. K equal to 1 I am taking for now for simplicity. Transfer function s is equal to tf of s. Then the MATLAB will know whenever you use s, that's for representing the transfer function that we have seen already, right? I've closed everything. Okay. Okay. Now the phase margin should be greater than 30 degree for values of k. That k value we have to see. First, we will look for the phase margin of this original system. We'll plot bode of this. Bode of TF1. So this is your transfer function. Here, this is your transfer function, and the bode is getting generated. So this is your bode plot. Now we want to see the value of k. We want to look for the value of k so that your phase margin is greater than or equal to 30 degree, right? So for phase margin to be 30 degree, we have to find the phase first. So if you right click on your bode plot and characteristics all stability margin. If you choose this, let me repeat again. Right click, characteristics, all stability margin. You have to select this. If you select this, the bode will show you the phase margin and the gain margin in your magnitude and phase plot. If you click on this, you will see gain margin is 64 at frequency of 8.94. Is closed loop system stable? Yes, it has told that it is closed loop stable. For now, the question is rotating around phase margin should be greater than 30 for what value of k. So now the gain margin is 64. Let me see the phase margin. This is 4.58, right? But we need the phase margin should be greater than 30 degree. So how do you usually calculate? The phase margin should be equal to 180 degree plus the phase at the grain crossover frequency, right? So here the other way around we are going to calculate. So the phase at the gain crossover frequency we want to find. So it will be minus 180 plus whatever phase you need, phase margin you need. That is minimum 30. So I am calculating minus 180. Let me tell minus 180. Usually your phase margin formula will be equal to 180 plus phase at gain crossover frequency. So now we want to find the phase at gain crossover frequency. So it should be minus 180 plus your phase margin, whatever has been asked in your question. Phase margin is 30. This should be minus 180, right? The phase margin is 30. So the overall should be minus 150 degrees. Now we have to look at the magnitude corresponding to the phase, that is minus 150 degree. Where the minus 150 degree will come here in the plot. One 50. Somewhere here, right? This is 180. It's 185, 200. Oh, sorry. Above it will be. It's minus, right? 150, 50 slightly, 151. It's 149. Somewhere between this, I have to find. Okay, it's around. I couldn't choose properly 150, but it's around 149 to 151 in the mid. So now the frequency for this phase is 4.19, right?
Yes, ma'am.
So this is between 4.19 to 4.48. So whatever frequency you choose between this 4.1 approximately to 4.5, that will be of the correct answer. So in the option, we look for this value. Omega between 4.1 to 4.3, whatever. Okay. This is correct answer, but why it is correct means this is greater than 4.3, then the 4.1 range won't come. This is less than zero point 0.8, this also won't come. This is also greater than 4.3, so this is the only option that is in between 4.1 to 4.5 approximately. So first option is the correct option, right? Now moving towards the second question. So I hope you understood, like the problem asks for value of k. Wait, delete all, won't be there. Okay. The problem asks for the values of k for the phase margin greater than 30 degree. Greater than 30. So how do we calculate that 30? You should not look for the value that is at 30. You should first make the calculation, that is phase margin equal to 180 plus phase at gain crossover frequency. The idea is to find the phase crossover frequency corresponding to that magnitude. So at the phase crossover frequency, it will be minus 180 plus whatever phase margin asked in the question. Once you find the frequency, that is the frequency that is corresponding to your k or phase margin greater than 3. Okay, right. Now the second question is, what are all the values of k that will yield a phase margin of 330 degree using bode plot? Okay, there are two values of k, k1 and k2, such that k1 should be less than k2, at which this is possible. Okay. For what values of k? K can be any range, right? From one point to another point, k can be any range. So here they have asked the frequency. Now we are going to find the k, exact k values for that. So they can be the frequency range we found is from the 4.1 to 4.5 approximately. So now we are going to just translate this in terms of a gain. For this 4.1, how much will be the k? For this 4.5, how much will be the gain? This will be between 30 phase margin, right? So the idea is to calculate that required phase margin. This required phase margin can be obtained either by shifting the magnitude plot or the phase plot. Both ways you will find. So in our case, what we are going to do is we will try to shift the magnitude plot, as we will find the change in the value of k, and that won't alter the phase plot. The phase margin can be 30 degree now. If the frequency is around minus 150, that's what we found. Now, the bode plot should take a 0 decibels at this frequency, because the value correspond to that in decibels is 0. Now we found minus 4.1 somewhere around here, right? 5.150 where it is. 155, 153, 150. Yeah, we found 150. That frequency corresponds to 4.4 will be 150. If you see the same frequency 4.4 here, the magnitude of the gain margin is, magnitude will be minus 54. Just you 4.1, it is for 4.1 frequency, the magnitude is minus 53.4. For 4.5, the magnitude is minus 54. So previously it was, how much I say, 52. 4.1, it is 53.4 to 54. So around 53 to 54, your magnitude will be correct. So we will be giving little more frequency range. Maybe the correct answer, since this is like a approximate design and it is also asymptotic design, we won't look for exact value every time, but we will give some frequencies like around 50 to 55 will be correct, or 47 to 55, whatever ranges you find within this would be correct. Some frequency range we will give. So for this, around 51 to 54 will be the correct gain value for this. Problem 2, what is K2? Okay, if I take 51 to 54, then my gain value will be 54. don't look about this. This is wrong answer. But the value of K2 here is the maximum margin. Since K1 should be less than K2, right? So, sorry, it's in minus, no? So you should consider that the lowest value is greater one. Minus 51 is the correct answer for this. Minus 51 to minus 54 is the gain value range for the question 2. Fourth question is, in problem 2, the magnitude plot is different for values of K1 and K2. Find the plot which has higher bandwidth. What is the value of that bandwidth? Magnitude plot is different for values of K1 and K2. Okay, we will first put K1 and K2, 51 and 54, and we plot the bode plot, and the magnitude will have a very little difference. Find the plot which has higher bandwidth. Okay, in which plot has the higher bandwidth and what is the value of that bandwidth? That's what the question is. Right. Now, let's take 51 to 54 for that. Okay. Okay, one thing I missed here is this K2 has been asked in terms of decibels. Okay, so you have to do that 20 log of 50 minus 51. That answer will be the correct answer. And then here for this, we will plot both bodies. For here, we have considered k equal to 1. Now we are going to put k equal to 50, maybe 50 and 54 we'll try. So we'll see some little more difference. K equal to 50, k equal to 55 or 54 I would. Because for 55 it went ahead. No? We'll plot both plots in the same plot so that we will get to compare. Hold on. Figure right. Okay. There isn't any big difference. That's why it was showing like this. If you look closer. Okay, wait. If I put k equal to 48, okay, that will say. So there is not much difference here between k equal to 48 and 54. Okay, this is the actual figure. Why it is always showing figure 2? Right, now we got it. Now I want to see the all stability margin, gain margin and phase margin. So here it is. Gain margin is 30, phase margin is 29. Okay, let me plot it in a separate plot. I don't think this can do. Okay. This is for face margin 54. This is for face margin. Like left hand side is 48. Right is 54. If you have any doubt, please let me know. Okay. I stop it then and there. Why are we doing this? How to do this again? If you want me to repeat, let me know.
Yes, ma'am.
Okay. Now if I look for the stability margins in both plots separately, left I have considered k equal to 48. Right I have considered k equal to 54. Now the gain margin is 30.5. Here, face margin is 29. Whereas this is also 30.5 and this is also 29. There is no big difference, right? It's almost equal. 8.94 everywhere it is same. So there will be only one bandwidth. You cannot really differentiate it. Bandwidth will come when you look for the frequency at minus 3 decibels, right? So at magnitude plot, if you look around minus 3 decibels, minus 2.74, minus 3 exactly it is. Okay, 0.968. That's the frequency we found for bandwidth. Okay, that's it. If it has been asked in radians per second, it was given in radian per second, right? But we have gotten it in degrees. So just make a conversion from degrees to radians per second. That's it. That's the answer for the bandwidth. So while you're solving your problems, okay, it's also given in radians per second only. It's minus 3 here in minus 3. What you will get? So you can take the same as it is. Minus 3 minus 3. Yeah, it's nearly same. Around 0.96. Okay. Right. Why we are not getting this is because we have put the k as it is. It's not in 20 log of. We haven't considered 20 log of. So it should be 20 into log of. So it should be 20 log of 48. Same 48, but it should be considered in decibels, right? So this is the mistake we are doing. 20 into log of 54. Now we'll see. This is for 40, this is for 54. Okay. If I find the stability margins for both plots, here it is gain margin 26. Here gain margin is again 26. Why? Phase margin has changed 34. How come? Let's check once more. Minus 3 it is 1.3. From Veena. Okay. 20 log of K2 is 20 log of K is 54. It should be 20 log of K is 54. Uh, it's 10 power. 10 power 54. No. Okay. Wait. 1. Okay, the problem here again is 20 log of 40, 20 log of k1, that is equal to 48. This is 1k. 20 log of k2 is equal to 54. This is another k. I have put it here, but it should be equal to, like, if you want to calculate in decibels, it should be here, right? So the k1 of decibels is equal to 48. That's what we found there. I should have not confused this with that. So the 20 log of this gain value is the 54 that has been found from the bode. So we have to calculate that like this. Now if I find log k1 equal to 48 by 20, 2.4, 10 power 2.4 it is. 251. Okay. Then this is 54 by 20, 10 power 2.7. This 501. Okay, this is 251, this is 501. So actually the K should be 251. That's why we don't get any visible difference there. 501. Right. So this is the updated value. So your K1 should be like this and your K2 should be like this. So from the bode plot, the previous question answer first between 50 to 54. We take 48 to find the difference, big difference. But 50 to 54 in bode or in log magnitude, it seems to be very small. But when you convert that into this original magnitude, it has very big difference, right? So when you find the bode plot between these two, you will, I hope you will get difference now. So if I find this, all stability margin, it's not responding. Okay. Characteristics, all stability margins. Here also characteristics, all stability margins. Now if I see gain margin is 26, it's also 26. Maybe the bandwidth will be changed. For -3 -3 decibels frequencies. I don't think this has changed. Okay, now it's 251. So that's all. Okay, silly mistakes. Okay, now,
Ma'am, in the code actually that plot is having k variable, so that could be an issue.
same K variable. Yeah, yeah, that's right. That's right. Yeah, that's right. Oh, this is K based on rat. It is coming, right? Yeah, it's stick. Right. It has changed. Now we look for minus 3 decibels. Okay, it's around 3.3. The frequency is around 3. Sorry, we have to look for the magnitude, right? Ah, magnitude only MC. Minus 3. It is. The frequency comes around. Oh, sorry. Charge went down. One minute.
Yes, ma'am.
Okay. No, there's minus 3. Minus 3. Screen is visible, right?
Yes, ma'am.
Okay. Now the frequency here is 3.4 around for minus 3 decibels. Okay. Here if I look for the frequency, magnitude minus 3. Okay. Approximately it's around 5.4, between 5.4 and 5.6. Let's take 5.5. Okay, somewhere around 5.5. Okay, that's the frequency. This is 3, this is around 5.5. So overall frequency for these two. Okay, see around 5.5 for the K2, then highest magnitude. That's what the question has been asked. The higher magnitude, the higher the gain, higher the magnitude. Then consider a system. Fifth question. Consider a system with open loop transfer function in unity feedback configuration. What is the phase margin of the system? So how do we find the phase margin? We know the formula and all, but in MATLAB, as I said for the first problem, you'll just look for the all stability margin. If you turn it on in the bode plot, you will get it. I'm just closing all the figures. So answer function is this format. So it will be TF2 is equal to um, let me calculate this. It's in fraction, doesn't look good. Okay, let me put it in this way itself. S into S by 1.4. Okay, it's better to calculate. Let me calculate it. Maybe that won't be visible in the camera. I'm doing it in my iPad. I will spell it, okay? S into S by 1.4 plus 1 into S by 3 plus 1. I'm taking this 1.4, I'm multiplying with 3 and 1.4 inside. So it will be 1.4 into S into S plus 1.4 S into zero point 0.4 S. And I feel this is also too much. We will do that straight in MATLAB itself. S by 1.4, it takes a lot of time. Into S by 1.4 plus 1 into S by 3 plus 1 whole. 1 opening. 1 is for the whole. This is for this. And this is for this. This is for the whole is there for this. Okay. And this section creates a problem that means no, it came out good. Okay, this is the transfer function given for this fifth problem. Then the question is, what is the phase margin? Right, straight away we'll plot the bode of TF2. This is 3F3. I will take. Okay, run section. Run section is to run the section alone, particular section where you put this double exclamation. What is this percentage sign is there? No, then it creates a separate section. Okay. And this is gain margin is minus 7.3, phase margin is minus 19.9. So for the fifth question, the phase margin is minus 19.9 is the answer. We have follow-up questions. In problem 5, what is the gain margin? We already found it. It's minus 7.13. Accurately, we are also getting here minus 7.13. Okay. And problem 5, the closed loop system is stable or unstable. That also we can get from this diagram itself. Here it will be told like closed loop system stable, no. So the closed loop system is not stable for any values of k you choose. That's what the meaning here is. Eighth question, for the system in problem 5, design a lag compensator with unity gain of the form, this form. Your compensator or the controller, whatever you are designing, should be a lag which is of the form Ts plus 1 divided by beta Ts plus 1, where beta will be less than 1 or greater than 1 for lag compensator.
Greater than.
So the phase margin is greater than 40 degree. Okay. First criteria is your phase margin should be greater than or equal to 40 degree. Since the addition of lag compensator modify your phase, we are for compensation we are adding little more 10 degrees. So the overall your design should satisfy greater than 50 degrees. Okay, greater than or equal to 50 degrees. You should consider while designing. You should take 50 degree as your at least phase margin. Then what should then be the new gain crossover frequency under these conditions, right? First we will find what is the actual gain crossover frequency. Gain crossover frequency occurs at phase margin, right? So the frequency at which the phase margin happens is 3. Phase crossover frequency is around 2. There is no much difference, right, for this particular problem. Now we want to design a lag compensator so that I will get like after designing the lag compensator that satisfies greater than or equal to 50 phase margin, what should be the new gain crossover frequency? Your phase margin will also be shifted because we minimum criteria is 50, so that should be greater than 50, right? Now it is how much it is minus 19. if you design it to greater than 50, this will be changed. Your gain crossover frequency will also change. Now, the actual value you got is minus 90. But the phase margin you require is 50. So, how we will calculate? We did for the last problem, right? Phase margin equal to 180 plus gain phase at gain crossover frequency. So the particular right hand side, if you want to get, it would be minus 180 plus 50, minimum 50. It should be minus 130-degree compensation we have to do, right? 130-degree difference we have to find. So the frequency we have to check at this value minus 130. We have to like make some changes. So we will look at minus 130. It's here somewhere. The frequency at which minus 130 is 0.712 radians per second. So that is your new gain crossover frequency for minimum of 50-degree gain margin. So if your gain margin is 50-degree, this point will be shifted here. So the new frequency of your gain crossover frequency will be 0.712. That's the problem. See, that's how easy it is in designing a compensator in MATLAB. But if you want to do the same using the formula, you have to find first you have to find the phase margin. You have to draw the bode plot, find the phase margin, and or you have to check a different cutoff frequency WC1, WC2, and all, and then you have to find this frequency at which it is happening, right? Hello, ma'am. Yeah,
Yes, ma'am.
yeah, I can take it there. No problem. Excuse me. Give me 2 minutes.
Yes, ma'am.
Am I audible?
Oh, yes, ma'am.
Okay. Right. We found the gain crossover frequency, new gain crossover frequency, right? The next question is, what is the magnitude in dB at this frequency? It's very easy. We can just calculate this frequency, how much we found. Minus 130, it is 0.73. So the corresponding magnitude at zero point 0.7 is 21 around. Around yeah, 21 degree, 21.8 if we take. That's the corresponding magnitude, but this is not the answer we are looking for. It should be of 20. Okay, in decibels only they have asked, right? In decibels it is 21.9 decibels, but in actual magnitude if they asked, you should convert this to 20 log of that k equal to 21. Then you have to find the k back from the value as we did in the previous problem. So be careful what magnitude has been asked, whether it is in decibels or it's in actual magnitude, not in logarithmic scale. So that's how you have to calculate it from there. So the next question is, right, what is the value of beta in the compensator? Now we know we have given with some compensator variable there, no? Like GC equal to this method they have given. First, if you want to find the beta, straight away with the formula we can do, or else we have to find the transfer function from the asymptotic bode plot, and then we can find the based on the time constant we can calculate the beta out of the transfer function. Two ways we can do. Let us go with the easiest way. The first way we can easily do that is using this formula, where the magnitude at your gain crossover frequency, that is new gain crossover frequency that you designed a lag compensator, right? That is it. Your new gain crossover frequency is some zero point 0.7 we found, right? And the magnitude corresponding to this magnitude in decibels corresponding to this gain crossover frequency is 21.7. Now, what are they asking is the beta value. How this is related to this? 20 log of 1 by beta. Wait, 20 log of 1 by beta equal to your magnitude, phase margin magnitude. This is your, sorry, gain margin, right? When you shift the lag compensator, this should be your gain margin. So this should be equal to your magnitude at which your gain crossover frequency happens. Now, then we want to find the beta. So log of 1 by beta equal to 21 by 20. It's 1.08. Now 1 by beta is equal to 1.08 by 20, 0.05, 0.05. Then beta is equal to 1 by 0.05. It's 20. Beta is equal to 20. I think that's correct. No, why? Where did I make mistake? Correct, right? Whatever we found is correct. It's 10 power log. Did I find 10 power somewhere? No, oh, that's why. Okay. See, in this, here I have made mistake. Log of 1 by beta equal to 1.8. 1 by beta equal to 10 power 1.08. Ah, it is 12, no? That's why. It's 12.002. Then beta equal to 1 by 12.002. Okay. The problem is here minus 130 corresponding. Okay, in the formula we made mistake. Formula should be minus of magnitude, right? It's not absolute value of this. So 1 by 20 log 1 by beta is minus 21. So log 1 by beta is minus of this. This should be 10 power minus of 1.08. Ah, then this is 1 by 0.08. It's 12.5. Okay, we got it. We got the answer. Now it is beta is of the compensator is 12 point around, and we are also getting similar to 12.5 or something. Given t equal to 10 and taking the value of beta obtained here, what is the phase margin of the compensated system. Now we know the beta value and t value they have given here. So we just have to put that in the transfer function and add it together to the original transfer function and to find the bode plot for that. That will give me the bode or phase margin of the newest one. So my compensated system would be only the compensator system they have asked me to. My compensated system. Oh, I can T compensated. I will take TF off, or I will take is equal to what is that answer function? It is TS plus 1 by beta TS plus 1. T is 10. Then TS plus 1 is 10 into S plus 1. It's 1 above numerator divided by beta is 12.5 into 10, it is into S plus 1. So this is the compensator. So original overall system will be TF3. We have found 3F3 is our original loop transfer function, right? TF3 into TF compensated. This is the control compensated, lag compensator we define. This is the overall system. So if I find the bode of
In
TF,
line, there is a type.
there is a,
Type one underscore is there.
okay, here,
No, no, line 32 is the typo.
line 32 is a typo. Oh, underscore is, okay, thank you, thank you. And this shouldn't be there. This will create a error. This is for annotation. Right. Now if I find the bode for this, I will create a new figure. This is the overall bode plot of the compensated system. System after compensation. So the gain margin is 13 here, phase margin is 42 here. So what was the question? Phase margin only they asked. Gain margin, okay, phase margin. Phase margin is, and next question is gain margin. Phase is 42.7, gain is 13.9 we are getting, right? Both are nearly same. Now, what are they asking is the what is the velocity error constant kV of the compensator system? Now you have the overall transfer function. This is the overall transfer function we got, right? Let me type it here. This is the overall trans of not comp. This is the compensator transfer function. Overall is this here. It's of 10 power s power 4. 420 s plus 42 divided by 125 s power 4, 551 s cube, 529 s square plus 4.2 s. There is no constant term. So this is the overall system. Now you find with this transfer function, you try to find the velocity error constant of the compensated system. How do you do that? Just put all this transfer function s into the overall transfer function. Try to take one s out here from here. One s, if you take s common out of this, one constant will be there, 4.2 will be there, above 42 will be there. So one s and one s will get cancelled. Putting final value theorem, this will go to 0. All other terms will go to 0. You will only get 42 by 4.2. Then 42 divided by 4.2, it is 10. Your kV is 10. Whereas the error constant kV is equal to 10. Bandwidth of the compensated system. Just look for the same at minus 3 decibels. Magnitude at frequency at which minus 3 decibels. This is 0.97. Okay, around 0.9 it will be. Then a lead compensator of the form is designed such that, yeah,
When we say bandwidth was
uh,
what does it actually mean here?
Okay, it's a kind of quantity or physical representation we want to say. When, for example, if in time constant we would calculate at 60 percentage of the time, right? It's because it will go zero after that. Similarly, in frequency domain, we will look for a particular physical quantity at a magnitude at which it is minus 3 decibels. Whenever the magnitude is at minus 3 decibels, so that's how it reaches or it loses all the energy and comes to the steady state point in a physical manner. Equivalently, in frequency domain, we would call that as a minus 3 decibels. Whenever the frequency comes to the the frequency corresponding to minus 3 decibel, we call that as a bandwidth. That is a maximum operating frequency of the system, that we can say like that.
Oh, okay.
For example, if bandwidth, usually what we will say for a rainbow or something, this is the bandwidth of this, because the rainbow colors will range from V to R, right? So that is the bandwidth of that. For every color, there are some bandwidth for from this frequency to this frequency. This is the same thing here. It's a operating frequency range we are seeing.
Oh, okay.
Right. Now, this is next the lead compensator design. I will do this, solve this here since the time has passed. You can come and see the live session later, or you can be here. I will just complete this until this part. Okay.
Okay.
Right. We are also doing a lead compensator design, which is of the form TS plus 1 by lambda, sorry, alpha TS plus 1, where alpha will range from 0 to 1. And it's designed such that alpha is equal to 1 and T equal to 1. Straight away, they have given that no need to find all those things. What is the maximum phase angle introduced by this compensator? Okay, let me, T is 0.3, alpha is 1, right? We will do a new compensator. Let me call this a slag. We will do new compensator, that is lead, which will be of T is 0.3, yes, plus 1 numerator, denominator is 1 into zero point 0.3 into s plus 1. It is correct, right? 0.3, 1 into s plus 1. What is the maximum phase angle introduced by this compensate? Now we have to find the phase angle has been asked, right? Okay. I don't think you can find it here, but let me try. TF overall lead is equal to TF3 into TF compensator of lead. Now if I put up here body of TF overall lead, then finding the phase margin and gain margin of this. The question asks us what is the maximum phase angle. Phase angle, how do you find that? It's from the formula we can find. Okay. And let me calculate it using the formula. It should be, how do we find the maximum phase angle? Phi m is equal to sine inverse will come, right? Sine inverse of some 1 minus alpha divided by 1 plus alpha. Okay. Then we can find it straight away. I guess this is the one way. I don't think any bode plot you can find from this. 1 minus alpha is zero point 0.3. Oh, point is 1, right? Then this will be 0. Alpha is 1. If it is 1, I don't think this is correct. Okay, actually, this is a typo. This is not 1. It's supposed to be 0.25. Okay. 1 means then it is sine 0, 0. Everything is 0, right? We cannot get anything out of it. So alpha we will consider it as 0.25. If it is 0.25, it is 1 minus 0.25 divided by 1 plus 0.25, 0.8. Sine inverse of, how do we, I don't know how to do sine inverse in MATLAB. A sine, okay. A sine of 0.8, 0.92. That is the maximum phase angle you would get. Is it so? No. 1 minus alpha is 0.75 divided by 1.25. 0.6. A sine of 0.6 is 0.64. How come? Rate into degree. Ah, that's in radian. So in degree, if you calculate, it will be 36 degrees. So it will be around 36 degrees. That is the answer. Maximum phase angle. So the things to learn behind this is a maximum phase angle can be calculated from this formula sine inverse of 1 minus alpha by 1 plus alpha, where alpha is the given parameter in your lead compensator. What is the frequency at which the maximum phase occurs? This also has formula that is omega m is equal to 1 divided by t into alpha root alpha it is. So SQRT of alpha. Okay, this is the maximum phase or frequency at which this maximum phase angle occurs. So it will be T is 0.31 divided by 0.3 into SQRT square root of 0.25. 6.66 around. That is the maximum frequency at which this maximum phase angle occurs. The next question is, what is the magnitude at the frequency obtained in problem 16? Okay, we have to look for 6.6 magnitude here. Sorry, 6.6 magnitude. I'm getting confused. 6.6 is what? Frequency, right? At this frequency, we have to look for 6.6 frequency where it is. Somewhere here. Mm. Minus 18 around. That is the magnitude. And problem 15, if Z and P are in 0 and the pole of the compensator, which one of this following is true? If Z and P are the 0 and pole of the compensator, okay, then which of the following is true? This needs a little. I want to solve it, so I will switch to iPad and solve this question. In problem, what they have asked is, Ts, it was given Ts plus 1 divided by beta, sorry, alpha Ts plus 1. That's a compensator or lead compensator format. In this question, what are they asking is, if Z is the 0 and P is the pole of the compensator, which of the following is true? They have given four options. So considering our compensator is in the form is that S plus C, S plus P, then if it is like this, then how can we do this? This will be S plus 1 by T divided by into T divided by alpha Ts. S plus 1 by alpha Ts, sorry, S plus 1 by alpha T into alpha T. So it will be 1 by alpha into S plus 1 by T divided by S plus 1 by alpha T. This is in the form of S plus Z by S plus P format. Right. Now, in general, for a system like this, S plus Z into S plus P, the phase angle phi will be given by tan inverse of omega by Z. Absolute value of Z minus tan inverse of omega by absolute value of P. Now, to maximize this phase angle, if you want to make it maximum, we will find the derivative with respect to T to be 0. So if find the derivative of phi with respect to omega and equate that to 0 to maximize. This is a common practice, right? When you want to find the maximum value of this, we will find the derivative, and derivative will look where is the maxima or minima of that. That's why we want to see where it is maximizing. So we are finding the d phi by d omega and going to equate that to 0. So this will give me d by d omega of the overall function tan inverse of omega by z minus tan inverse of omega by p. It's little not easy to calculate. If it is with respect to omega, tan inverse means you will get it like this, right? Tan inverse of A is equal to 1 by 1 plus A square. So this will give me 1 by 1 plus omega by z the whole square into, with respect to omega, see if I calculate d by dx of tan inverse of ax means it will be 1 by 1 plus ax square into a, because derivative with respect to x should be taken, right? So this will be 1 by z will come minus the same thing again for this 1 by 1 plus omega by p whole square into 1 by p. Right. Now I am going to equate this to a 0. 1 by 1 plus omega by z the whole square into 1 by z minus 1 by 1 plus omega by p the whole square into 1 by p equal to 0. Equating this 1 by z, 1 by 1 plus omega square by z square equal to 1 by p, 1 by 1 plus omega square by p square. This will give me 1 by z square by z square plus omega square equal to 1 by p square plus omega square. So this and this will get cancelled. Z by z square plus omega square equal to P by P square plus omega square. This is giving me z into P square plus omega square minus P into z square plus omega square. Zp square plus z omega square equal to z square p plus p omega square. If I take omega square common, this term and this term will come z minus p is equal to all other things on the z square p, that will be minus zp square. So omega square is equal to, I will take p z common because both terms are there, z minus p divided by z minus p. This will get cancelled. Omega square is equal to pz. So this can also be written like absolute value of p into absolute value of z. So omega max. That's what we are asking because we have equated that to zero long back, right? So it gives us the maxima of that. That will give you root of p z. So if this is in the option, then that is the correct option. So that's it for today. So today we have learned how to design a compensator based on the bode plot. We did both lead compensator and lag compensator base. So whenever you were asked to find or design any compensator, just find the phase margin shift and look for the corresponding frequency. Move your cursor towards that new frequency, and that's the compensator system's minimum phase margin and gain margin.
So this design assignments they will be given when, ma'am?
In next week.
Okay. What weightage do they carry, ma'am?